How are you? Any questions? Ready to start? Who's ready to start? 2 or 3 people. Okay, so for the past 5.5 weeks, we've been looking at variables, memory, pointers, dynamic allocation, all things having to do with representation of data in programs. And we're not going to switch to looking at control flow, which control flow is about how how a programmer decides what code will execute next. We're going to look at this. We're going to look at first static control flow, which is what we're doing now this week, and then dynamic control flow later. Part of static control flow is procedures, so we'll bring in procedures and we'll come back and do a little bit more on variables. Today and Friday, looking at static control flow. So examples of static control flow programs are procedure calls, as I just mentioned, for loops, if statements, stuff like that. There are ways the programmer controls, as I said, what happens next. Now, if you don't have control flow directly specified, the implicit control flow is just sequential. So your program executes statements in order, left to right, top to bottom. And it's when it gets to things like for loop, which we're going to look at today's for loops, then something different happens. So here's an example in C and in Java of for loop. So the C is on the bottom. This is sort of the beginning of all for loops look like this. It has 3 parts separated by semicolons. The first part is a variable declaration, and now in the modern versions of C, just like in Java, that declares a variable whose scope is just inside the loop. So that variable I is only accessible inside the loop. What do you think? If it was like this. You can do it either way. So if it was like that, it's inside the loop. If it's like that, that's just a global variable that's accessible inside the loop and outside the loop. Either way, so it's either just initialization or declaration with initialization. The second component is a statement that's evaluates to true or false. So it's a predicate that determines whether or not the loop should continue. And that has to be checked at the beginning of each iteration. So when that's false, you don't do the body and the loop stops. If it's true, then you do the body, and then you go to the next iteration of the loop to see if it should stop or continue. And then the final thing is the step. So a very common way to do loops is that you have a variable that you're counting, you start at 0, you count out to some number, and you increment each number. In Java, there's this kind of loop. It's exactly the same, and there's also the for each loop. The for each loop, you remember, is implemented by classes using a design pattern. What was the design pattern? Iterable or iterator design pattern. Okay, so we're not going to look at that. We're just going to look at this kind of loop. And before we get into this, so what we're going to do is we're going to look at how that loop would be compiled with machine code, assembly language, and we'll add some instructions to do that. But before we do that, I have here 2 procedures. They do the same thing. The top one, you have 2 parameters that are arrays and a number, and it uses a for loop like I just described, and it copies from one to the other. The bottom one takes 2 pointers in a number and has a while loop where it decrements that number until the number is 0. Each time, it decrements, it first evaluates the number. Is the number 0 yet? No. If it's 10, if it's 9, if it's 8. Yes, if it's 0. So if it's not 0 yet, then the while loop will continue, because values that aren't 0 are considered to be true. When it gets to 0, that's considered to be false. So that will do that body of the loop n times. Right, so if that is 1, you do it once. If be 1, it's not 0, and you decrement it, minus minus means decrement. Next time you loop, and 0, you stop. And then there's this weird thing here. What is that? This is just review. But I'm making a point. What is that equivalent to? Well, you know, you just don't have a way to say. So it's like this, yeah, so star D equals star S, and then D equals D plus 1, and S equals S plus 1, which would also be the same as if I had this int I 0, and then in the while loop, I say D plus I equals S plus I plus I equals I plus 1, which of course is the same as this. So this is what's listed there. What it really means is what's in the code above. Everybody, any questions about that? You should be able to read what's below. Can you read it? Okay, so now the question, the reason I bring this up here is to ask this question: which one should you write? So who prefers the first? They're equivalent, writing one. Who prefers the first one? Who prefers the second? It's astounding. So the same thing happened this morning. This is the first time. No one has ever voted for the second one. Not even you. I wouldn't even you vote for the second one. Yeah, so the second one you can do, it looks clever. And so a lot of times C programs are tempted to do the things that look clever, but you all realize that what's more important is to write the things that are clear. So this pointer syntax for arrays and the auto-incrementing, as part of the thing, you can do that. You need to be able to read that, because some people have written code where they thought they were clever, and you're going to be forced to read it. But when you write code, you should be writing it like it is up there. Can anybody explain to me why? Why is the top one better?
It's more clear.
It's more clear, and why is it more clear? Yeah, both. So you can see that it's an array, and you can see that it's a for loop. So the reason it's better is because there is structure in what you're trying to do that you make explicit in the code that you write. And we get used to seeing, like the first time you saw that, it wouldn't make any sense. But when you get used to these stylistic things in a programming language, showing you the structure, then it's very easy to see what that is. So that's an important idea that I'll sort of come back to at the end of class today when we're looking at assembly. So you got to read both, but you should never write the one on the bottom. All right. So now into a loop. We're going to implement it in machine code. We have already in the instruction set architecture instructions that access memory and instructions that do math. And the question here is that enough? Do we need to add any more instructions? And let's start with this specific piece of code. So this code has a statically initialized array, and it loops through that array, summing up the values of the array. And the question is, can I implement that array? So could I compile that into machine code, assembly code, without adding any new instructions? Or am I going to be required to add a new instruction for that particular loop? Okay. Discuss that with each other. Do I need a new instruction or not?
The ISA, the branch from this row, the branch from the
Okay, so who thinks I need to add a new instruction? Who thinks I don't? Who's not sure? So the first and third categories are evenly split, and very few people got the right answer. I don't have to add anything. Now, why is that? Well, it's because the compiler actually knows how many times the body of the loop is going to execute. So it could generate this code instead. This is called unrolling a loop. I'll just list out, when I compile the loop, each individual body of the loop as a separate statement. Now, it's more code, right? So I have the body listed in the top is just listed once. On the bottom, it's listed, I don't know how many things are in that array. Is it 10 things? I'll list it 10 times. And if it was 100 things, I'd list 100 of them. But there's no problem. The compiler can do that. And we don't need any extra instructions. Right? So, but the intuition you had that, yeah, I think we're going to need an extra instruction comes from the fact that not all loops execute a statically known number of times. Okay, so here's the general form of a loop where you have, as a general form of a specific kind of loop, right? So this is a really common one, where this goes through the loop n times. N's a variable. The compiler doesn't know n. So it needs to generate code that looks something like this. It says, okay, well first there's the green part that's initializing I. Okay, that's outside the loop. And then I'll have a label for the beginning of the loop. And the very first thing I do in the loop is say, don't do the loop and stop looping if I've got to the end. So I have to now compare something to n. Right? And then I have the body of the loop, which is the thing that's not circled there. And then I have the purple part, which is the step. And then at the end of the loop, I'll just go back to the beginning of the loop. So I'll keep the end always goes back to the beginning. I just keep doing that until I get to a point where the continued condition, which is in order, is false. And then I exit. So the things in red are new instructions. We don't have those now. We need an instruction, at least here, an instruction that will just always jump to some location. Right? Because the control flow here isn't sequential. When I get to go to loop, it doesn't just keep going. It changes and it now moves up to the beginning of the loop again. So that part of the control flow is this guy. Right? And all loops have that. All loops, you get to the bottom, you go to the top. And then I need another one, which is a conditional jump out. So if I just had the unconditional, you can always jump, not jump with it, then that's not enough. Because that loop would just execute forever. So I sort of go, if I don't have anything, then I can't loop at all. I can execute a static code, I can repeat it a static number of times, but I can't loop at all. If I just have the bottom, I'll just loop forever, I can't get out. So the crucial thing that we need is this conditional. Sometimes you go here, sometimes you go there. And unless an instruction set has that, it's not Turing complete. You can't, there'll be programs that can be computed that can't execute on this process. So this is the key thing about the Turing machine, which is our model of computation. We think anything that can be computed can be modeled by the Turing machine, is that it's infinite. It's that the execution is infinite. It's that you can take one simple state machine or one simple program and have that repeated over and over and over again, depending on the size of the input. And that's required. You can't, that's a fundamental part of computation. So we're definitely going to have to add an instruction. In fact, we're going to add 4 new instructions in order to do this. So the instructions have, yeah.
If for the loop, for example, if n was known, and if it's I plus equals b, for example, will the compiler still know how many times the loops are
So if, the question is, well, if the compiler can compute the value of n, and then anything you say after that, you said that if we add 2 rather than 1, could the compiler unroll the loop and avoid actually using looping instructions? The answer is yes. Now, as you make that more complicated, it maybe makes it harder for the compiler to figure out. You know, it has to know for sure what the value is. In the case of the previous one, the RAM, well, it was just a constant. But it's possible, you know, it's a variable, but the compiler can figure out, oh, that variable is always this number. And if it's smart enough to do that, it can avoid. And in fact, compilers do unroll loops in order to make code run faster. So, in slightly different ways. Okay, so we're adding new instructions. We're going to add 4, and they have 2 different names. They do the same thing, but they have 2 different names. So, jump and branch. So we'll look at jump first. So let's say I have statement, and then I say jump L1, and then I have statement. And then somewhere down here I have L1 statement. The control flow is like this. You go execute these things, you get here, you don't do this stuff, you instead come down and execute that. Does that make sense? So let's think about what that sort of instruction does. What does it look like? Well, it has to say where you're going to jump to. And how do you say where you're going to jump to? If you name something, you're naming what? You're naming, you said PC, I'll come to PC in a second. You're naming the address of an instruction. So remember that it's like this. It's the CPU, and we've got memory. And the program is stored in memory. All the instructions are in memory. So that thing I just drew here is over here in memory. And if I want to change the control flow, I have to say, well, go get the instruction at this address rather than that. So this instruction is going to look something like this. It's going to be XX and then some address. And let's say that this is 0x, so 2000. This would be the number. Does that make sense? Now, branch instruction is semantically the same. Okay? So I have also possibly branch L1. It's implemented differently. And we'll come to that in just a minute. In addition, I have the conditional branches. So we have branch equal. And I list a register number that I'm going to test the value. So it might be, say, register 0 and L1. And what this means is go to L1 if the value in register 0 is equal to 0. And then the other one is branch and greater. Same thing, go to L1 if R is 0, but in this case it's greater than 0. Full instruction sets would have all the different versions of this. They'd have not equal, greater, equal, less, equal. They'd also have signed and unsigned comparisons, sometimes called above and below. This is all we're going to have. You can do all the rest of them with just these two. So that's sort of the minimal set. So focusing for a moment on these two instructions and the way they work, what you see is that we have only a comparison to 0. And usually the comparison we're actually making is to something other than 0, right? So in the loop, I'm comparing I to n. But in hardware, I have to compare I or something to 0. Okay? So that part in red there, that comparing I to n, has to be normalized into a comparison to 0. And one simple way to do that is if I'm counting up to I and I want to get out of the loop, which is what that's doing, when I hits a certain number, I might just subtract that number from I, and put it in a temporary variable, and then use that temporary variable as the comparison. That's what happens here. That's what we'll do in the assembly language. Another, can you imagine something else you could do? I can count up using I, and when I get to, let's say I'm doing to 10. So when I get to 10, I keep subtracting 10. So I start off with minus 10, minus 9, minus 8, minus 7, and that subtraction. I eventually get to 0 and then I get out. Right? So when I is equal to 10, I don't do the loop anymore, and I don't do the body loop. What's something else you could do? So another thing I can do is I can start at 10 and decrement until I get to 0. And so that's another great strategy. It's, if you do that, you might need to have a variable that's counting up, because that might be the index into an array, for example, and also a variable that's counting down. So another great way to do it. Okay. So let's look at what happens now in the implementation of these instructions. What do we have to do in the machine? And this is a bit of code from the Java instruction set simulator, simple machine simulator, showing the procedure called fetch, which you have up until this point completely ignored, and in fact you can continue to ignore it, except for what I'm going to say. Okay? So in the CPU class, there was a procedure called execute. And this is the one where you implemented all the instructions. And you're going to have to implement these 4 new instructions as well. And what I want to do now is talk about, well, what is that implementation going to be? In order to see that, we have to look at the fetch state. So the complete execution is like this. You do, in every clock cycle, you do a fetch, and then an execute. And then, the clock ticks. And you repeat that infinitely. So at the beginning of the execution of every instruction is the fetch stage. After fetch, then you do execute. You know what execute is. So what fetch does, as is shown here, is it fetches the next instruction. Okay? And to do that, it uses a register called the PC. So the PC is a pointer to code. It's a pointer, or where to put it. It's a pointer to one of these instructions in memory. Right? So this points to some instruction. That's the next instruction to execute. So what it has to do is go to memory and get that instruction. So that's what you see here. Is the very first line reads the value of the PC and puts that into an integer so we can use it. So that's the pointer to memory. It then does a memory read for 2 bytes. So now the variable ins, which is the byte array, stores the instruction. Now, some instructions are 6 bytes long. For example, the jump is 6 bytes long. This is the second one we have 6 bytes long. To know if it's 6 bytes long, you have to look at the opcode. So that's what happens next, is it looks at the opcode. If the opcode has a certain value, then it goes out and gets 4 more bytes. Okay? But either way, what it does also is advance the PC. So you see, just look at the case where you don't do that switch state. So you get the PC, you read from memory 2 bytes, then you add 2, and then you go all the way to the end, and you change the PC so that it points to the next instruction. So that's sequential control flow. Sequential control flow is just adding the size of the current instruction to the PC in the fetch stage, so that by the time you come back around again to fetch, it will fetch the next instruction. And this will repeat. So the next time through, PC is here, fetch this one, advance it to here, and so on. Does that make sense? Okay? So you can think about control flow like as sort of visually, it's like reading, you do this, then you do this, then you do this, and maybe it's a loop, so maybe you come back and do this again, and this again, and this again. So it has this very kind of intuitive, sort of graphical understanding. And it seems very different from the value of variables, right? The variable seems like, you put a number in, add something to it. But this picture shows you that control flow actually is the value of a variable. Essentially. I mean, it's not a variable in the program, but it's a storage location in the processor. So control flow, changing the control flow is really just changing the value of the PC. That register. So in the execute stage, when we're executing this instruction, and remember that this part here will have the name INSEX. I think it's EXT. Is that right? Maybe it's INSOPEXT. But that's a register. It represents the value of this part of the instruction. To implement that instruction, what do? Well, you just copy that into the PC to say PC gets INSEXT. Just copy that number in. So that you're executing this instruction. The fetch states move the PC to here thinking, well, you might just keep going. But then when you're executing this instruction, say, hang on, that's not what we're going to do. Next time through, get the instruction from here. So it changes the PC, so it stores the address of this instruction, and then when you come back around again to fetch, after executing the jump, you're going to fetch that instruction instead. Make sense? Questions? Okay, so you'll see that this jump instruction is 6 bytes long. It's a big instruction. Do we like big instructions? Who likes big instructions? Who hates them? No, we don't like big instructions. Why don't we like big instructions? Everybody, we sort of waved I waved my hands about it when we were of course. Well, this is right. So it sort of goes against the RISC philosophy. RISC philosophy is have as many instructions as small as possible. And what's the advantage of that? So the advantage of it is that going to memory, which is what you have to do to fetch an instruction, is slow. And so we want to use some techniques, and one of them is a cache, which I learned about in 13, so that we minimize the cost of getting things from memory. And just basically speaking, if you're getting smaller things from memory, whatever techniques we're using are going to work better. So if I have a bunch of small instructions, they'll fit better in the CPU cache. CPU. I'm going to use some techniques so that a lot of times the instruction I want, now it's in memory, but it's also here too. Right, that's a cache. And so, as I said, I'm sort of waving my hands about that, but small is better. So here I have a big instruction, and that is not so great. Now, if these instructions executed very infrequently, then it's fine, doesn't matter. Or if there's nothing I can do about it, then I just have to live with it. So let's talk about the first one. And let's look now at the control flow within a procedure. So this is the loop, right? The jump at the beginning, the jump at the end. and if statements, as an example. Are those going to execute frequently or not? If I counted up, I looked at every instruction that's executing and said, is this a jump, one of these jump instructions, or is it a regular instruction? How many, at what frequency would I see jump instructions? $10% of the time? Raise your hand. 0% of the time? 0 to 10, 10 to 20, 20 to 30, more than 40. It's probably between 10 and 20%. And the reason for that is it all depends on how good of a programmer you are. If you're a really good programmer, you write really small basic blocks. You just have 1 or 2 statements inside of an if statement or inside of a loop. So these instructions are actually going to execute quite common if you're following the style of programming where you have small, what are called basic blocks, the number of instructions that execute without a control flow instruction. So we do care about it. I mean, yeah, I'm waving my hands, but we do care about it. Now the question is there a way we could make an instruction that would jump, that would do exactly what this does, but maybe in some restricted cases? But be small, be only 2 bytes long. So can I do this? And then have a 2-byte number here. We'll just call it n. And to help think about this, let's give, so this address here is 2000. So we'll just change this now to a number. No, I actually don't want it to be 2000. I want it to be 1020. And let's say that this is 1000. So this is up here 1020. Fine, because I'm just jumping to that. Is there something else I could do to describe where I want to go that's a small number? So this number is big, right? It's either 4 bytes or actually in modern computers 8 bytes, because addresses could be arbitrary and not arbitrary. You have to 64 bits wide. So I need 8 bytes to store them. But is there another way I could say where I want to go that is just a small number?
Something like the offset number.
Yeah, so I could say, well, just go 20 from here. Right? So kind of something like this. Okay. Now this is going to be has to be a signed number because I need to go backwards as well as forwards.